Hello everyone, I am Dr. Krishna Sarker, Department of Electrical Engineering. Here in this session, I will be going to discuss about Jordan's canonical form, problem number 20. This is lecture series on state space analysis and lecture number 28. This is state space analysis, control system, subjects. So our problem number 12 by using Jordan canonical form. Example 12. Consider the following transfer function ys by us equals to s plus 3 divided by s cube plus 9s square plus 24s plus 20. So overall transfer function ys by us equals to s plus 3 divided by s cube plus 9s square plus 24s plus 20, where ys equals to system output and u of s equals to input of the system or reference input of the system. Obtain the state space representation by using diagonal canonical form or Jordan canonical form. Calculate state space equation, state matrix, state diagram, and signal flow graph, and stability of the system. Stability of the system. So our target state space by using state space analysis or by using Jordan canonical form, from this transfer function to state equations, state model, state matrix, state diagram, and stability of the system. This is our target. So step number 1, solution. The given transfer function is as ys by us equals to s plus 3 by s cube plus 9s square plus 24s plus 20. This is the transfer function where numerator terms are called zero position and denominator is called poles position. In this case, step number 2, for this system, an auxiliary variable is introduced such that the transfer function in the factorized form as, what is the factorized form? This is the factorized form ys by us equals to s plus 3 by s plus 2 whole square whole into s plus 5. So here repeated roots. Repeated roots means at s is equal to minus 2. One pole and s is equal to minus 2 another pole. So repeated roots in this situation, so we can apply Jordan canonical form. We can apply Jordan canonical form. So this is the partial fraction ys by us equals to, for s plus 2 whole square d11 by s plus 2 whole square plus d12 by s plus 2 plus d1 by s plus 5. This is the partial fraction ys by us equals to d11 by s plus 2 whole square plus d12 by s plus 2 and plus d1 by s plus 5. So calculate fast d11, d12 and d1. Then determine the system stability. Also draw the state diagram. So what is the d11 value and d12 and d1 value? Then s plus 3 by s plus 2 whole square s plus 5 equals to, this is the form, multiplying both sides by s plus 2 whole square into s plus 5. Multiplying both sides by s plus 2 whole square plus s plus 5. So left hand side cancel out, denominator terms only s plus 3. This is the s plus 3 equals to d11, s plus 2 whole square cancel out. This term cancel out, only s plus 5. This is the s plus 5 and d12. This is the d12 and s plus 2, one s plus 2 cancel and another s plus 2 into s plus 5. Then d1 into s plus 2 whole square into s plus 5. So s plus 5 cancel. Then only s plus 2 whole square. only s plus 2 whole square. Only s plus 2 whole square. So s plus 3 equals to d11 s plus 5 plus d12 s plus 2 into s plus 5 plus d1 into s plus 2 whole square. Calculate d11, d12, d1 coefficients. Multiplying s plus 2 and s plus 5, s square plus 7s plus 10, and multiply as this is the square terms, this is the square terms. So s plus 2 whole square equals to s square plus 4s plus 4, and this is equivalent to s square plus 7s plus 10. This is equivalent to s square plus 7s plus 10. S square plus 7s plus 10. Then comparing both sides, first s square terms, next s terms, and constant terms. Then calculate d11, d12, and d1 value. So first d12 plus d1 equals to 0. First s square coefficient. What is the s square coefficient? This is the s square coefficient. S square coefficient equals to d12. So this is d12. This is the d12 value. And next position, d1 coefficient, d1 into s square. So this is d1. And this is equivalent to 0. This is equivalent to 0. This is the first equation, equation number 1. Then s coefficient, comparing both sides, s coefficient. Constant value. First, next, comparing both sides, constant value. Left hand side, right hand side, what is the constant value? d11 into 5, d11 into 5. This is the d11 into 5. And d12 into 10, d12 into 10, d12 into 10. So d10 into d12. And this is the d1 into 4. So this is 4 into d1, and left hand side constant value 3. So this 3 equals to, again 5 d11 plus 10 into d12 plus 4 d1 equals to 3. This is the second equation, and then comparing both sides, s coefficient. What is the s coefficient? This is the d11. This is the d11 into s. So this is d11 and 7 into d12. 7 into d12. This is another coefficient, and third coefficient d1 into 4. So this is the 4 into d1 coefficients, and right hand side s coefficients 1. S coefficients 1. So this is the 1, right hand side 1. So equation 1, 2, solve equation 1, 2, and 3 and calculate d11, d12, and d1. This is the value. d11 equals to 1 by 3, and d12 equals to 2 by 9, and d1 equals to minus 2 by 9. This is the value of d11, d12, and d1. So what is the process? This is the process. First equation, what is the equation number 1? d12 plus d1 equals to 0. So d12 equals to what? d12 equals to minus d1. Just d12 equals to minus d. This is the equation number 4. And d12 equals to minus d1 in equation 2, and we get, just put, and we get put here just in this position. In this position, d1. This is the d1 value. So put here d1 equals to minus d12. Minus d12. So this is the next step. So 5 d11 plus 6 10 d12 plus minus 4 d12. 6 d12 equals to 3. This is equation number 5. This is equation number 5. And next step, then again put d12 equals to minus d1 in equation 3. In equation 3, and we get d11 plus 3 d12 equals to 1. So solve 5 and 6, we get d12 equals to 2 by 9, and put d12 equals to 2 by 9, then we get d1 equals to minus 2 by 9, and then d11 equals to 1 by 3. So the coefficient d11, d12, and d1 equals to 1 by 3, 2 by 9 and minus 2 by 9. Then the overall transfer function ys by us equals to, this is the overall transfer function. This is the overall transfer function. Then multiplying both sides by u of s. Multiplying both sides by u of s. Then this is multiplying by u of s. So this u of s cancel. Only y of s, and this side 1 by 3 s plus 2 whole square into u of s, 2 by 9 s plus 2 whole to the power 1 whole into u of s plus minus of 2 by 9 s plus 5 whole into u of s. So multiplying both sides u of s, then we get y of s. Then this is the very important part, because in this situation, this term us by s plus 2 equivalent to z1s. us by s plus 2 equals to z1s, and put here us by s plus 2 equals to z1s, then we get z1s by s plus 2, z1s by s plus 2, and us by s plus 5 equivalent to z3, Then next step, in this situation, z1s equals to what? z1s equals to us by, z1s equals to us by s plus 2, z1s equals to, this is the z1s value. Then multiplying, just multiply, and z2s equals to what? z1s by s plus 2. This is the z2s value. This is the z2s, z1s by s plus 2. So this is z2s, and z3s equals to us by s plus 5. So z1s equals to again us by s plus 2, z2s equals to z1s by s plus 2, and z3s equals to us by s plus 5. Then calculate case number 1, step number 4, case 1, A1, z2s equals to what? z1s by s plus 2. z1s by s plus 2, cross multiplication, just multiply this into this. So s into z2s plus 2 into z2s, 2 into z2s plus equals to z1s, taking inverse Laplace transform, and we get taking inverse Laplace transform, and we get, this is the first order differentiation terms, dz2 by dt plus 2 into z2t. This is the z2s. So after inverse Laplace transform, z2s equivalent to z2t, and right hand side z1s equals to z1t. This is the system input, and z22 equals to output, and z22 variable output, because z2t position and rate of change of z2t output, this is the velocity of the system. So when position differentiate, this is velocity, and velocity integrate, this again position, selection of the state variable. So this is the variable term. That's why z2 equals to, put z2 equals to x1. This is the state variable x1. z2t equals to state variable x1. Then differentiate both sides, and we get z2t equals to dz2t by dt equals to x1 dot. So put here, this is the z2 dot, and this is equivalent to dz2 by dt, and this is equivalent to this. So put here x1 dot, and next term x1 dot equals to what? x1 dot equals to x1 dot, this is x1 dot plus 2 into this is x1 equals to z1t. Then x1 dot equals to, just minus side change, minus 2 into x1 plus z1t. This is the first equation, state equation. This is state equation because left hand side differentiation term and free of differentiation terms right hand side. So this type of equation is called state equation. This is equivalent to x dot equals to x plus bu. This is equivalent to x dot equals to x plus bu. Then step number 4, case 2. Okay, what is the case 2? Z1s equals to us by s plus 2. again cross multiplication, Z1s into S, Z1s into S plus 2 into Z1s, 2 into Z1s equals to U of S. Again taking inverse Laplace transform, then we get US equals to UT and Z1s equals to Z1t and S into Z1s equivalent to dZ1t by dt. This is the first order differential equation, and this is Laplace transform, inverse Laplace transform, and all initial conditions are zeros. And again, U of t equals to reference input, Z1t equals to output, and this output variable because this output position, this is the position and this is the velocity, rate of change of position. So put Z1t equals to another state variable x2. Again differentiate both sides and we get Z1 dot t equals to dZ1 by dt equals to x2 dot. So this is the x2 dot and this is equivalent to this part, and this is equivalent to again x2 dot state variable, state x2 dot, and then we get x2 dot, put here x2 dot plus 2 into x2 equals to u of t. And what is the x2 dot? X2 dot equals to minus 2x2 plus u of t, minus 2x2 plus u of t. Then case number 3, step 5, case 3. What is the case 3? Z3s equals to us by s plus 5. us by s plus 5 and cross multiplication s into Z3s plus 5 into Z3s equals to u of s. Thus just s into Z3s plus 5 into Z3s equals to u of s. Then we get again taking Laplace inverse Laplace transform and we get dz3t by dt plus 5 into Z3t equals to u of t. And in this position, u of t equals to reference input and Z3t equals to output, and this output variable because this is the position and this is the acceleration. Again put Z3t equals to x3 state variable. Differentiate both sides and we get dz3t by dt equals to x3 dot, and this x3 dot equivalent to this x3 dot equivalent to this term. So put here x3 dot. This is equivalent to x3 dot and this is the equivalent to x3. So what is the state equation? This is the x3 dot plus 5x3 equals to ut, and simplest form x3 dot equals to minus 5x3 plus u of t. This is the state equation because left hand side only differentiation terms and right hand side free of differentiation terms. Then what is the state equation? The state equations are x1 dot equals to minus 2x1 plus x2 and x3 coefficient 0. So 0 into x3 plus 0 into u of t, and x2 dot equals to 0 into x1 minus 2 into x2 plus 0 into x3 into 1 u of t, and x3 dot equals to 0 into x1 plus 0 into minus 9x2 equals minus 5x3 plus u of t. Then the state matrix. What is the state matrix? Just put here this side, left hand side. This is the x1 dot to x3 dot. This is the x1 dot to x3 dot. So this is the state matrix x1 dot x2 dot x3 dot. And coefficient, first coefficient minus 2. This is also minus 2. Second coefficients 1. So put here 1. Put here 1, and third coefficient 0, and this is the 0. So x1 dot equals to minus 2 into x1 plus 1 into x2, 0 into u of t. So first equation satisfied. And second equation, what is the second equation? This is not x1 dot, this is x2 dot. x2 dot equivalent to what? x2 dot equivalent to 0. This is the 0, put here 0, and this position minus 2. And this position 0, then ut coefficients 1. So x2 dot complete, and again x3 dot, x1 coefficient 0, x2 coefficient 0, and this is the x3 coefficient minus 5. So ut coefficient 1. This is 1 in this position 1. So put here 1, and we get the state matrix. We get the state matrix. This is equivalent to x dot. This is equivalent to x dot, and this is equivalent to a plus Ax plus b into u. So A equals to this matrix, and this is the Jordan matrix, and this is the X matrix. This is B coefficient B, and this is U of T U, and this is the X. Why Jordan matrix? Because these two element repeated roots and only one r times repeated roots. Here r equals to what? R equals to 2. So 2 repeated roots, minus 2, and r minus 1, r equals to what? R equals to 2 minus 1 equals to 1. Only one super diagonal 1. So this is satisfied the Jordan canonical form, and this is the distinct eigenvalues or distinct roots of the systems. Distinct roots of the systems. So output, what is the output equation? What is the output equation? The output equation already proved. Ys equals to 1 by 3 z2s plus 2 by 9 z1s plus minus 2 by 9 z3s. Then taking inverse Laplace transform, and we get this is equivalent to y of t, and this is equivalent to 1 by 3 y by 3 constant, and z2t Laplace transform inverse Laplace z2t, and this is constant, and z1s z1t, this is also constant, z3s equivalent to z3t. Then put here x1 dot z2t equals to x1, z1t equals to x2, and z3t equals to x3. So this is the state equation. First coefficient 1 by 3, second coefficient 2 by 9, and third coefficient minus 2 by 9, x1, x2, x3. This is equivalent to y equals to cx. This is equivalent to y equals to c into x, where y equals to this matrix, c equals to this matrix, and x equals to this matrix. This is the output matrix. This is the output matrix. Then state diagram of Jordan canonical form. What is the state diagram? These three equations are state equations, and this is the output equation, and this is the state diagram. This is the state diagram. So first, x2 dot, this is the x2 dot. x2 dot equals to what? x2 dot equals to minus 2x2. x2 dot integrate, then this is x2. x2 dot integrate, then this is x2. And x2 feedback by and multiplying by 2, this is minus. So in this position, 2 into x2, 2 into x2, 2 into x2. So x2 dot equals to minus 2 into x2, minus 2 into x2 plus u of t, only u of t. This is the second part, u of t. So x2 dot equals to minus 2x2 plus u of t. Similarly, x1 dot integrate x1, and x1 dot equals to minus 2 into x1. So this is x1, this is 2 into x1, this is minus. So x1 dot equals to minus 2 into x1. x1 dot equals to, this is equals to minus 2 into x1, minus 2 into x1 plus only x2, This is the x2 part. So put here x of 2. Put here x of 2. Second equation also satisfied. Then x3 dot. What is the x3 dot? This is the x3 dot. This is the x3 dot. x3 dot integrate. Then this is x3, and x3 whole into 5. x3 into 5, and this is minus. So x3 dot equals to minus 5 into x3. Minus 5 into x3. This is also satisfied. So equation 3 also satisfied. Then output equals to what? 1 by 3 into x1. This is 1 by 3 into multiply by x1. So this is the 1 by 3 into x1. Second part, 2 by 9 into x2. 2 by 9, this is the x2. This is what 2 by 9. So 2 by 9 into x2 added, and again minus 2 by 9. This is plus minus 2 by 9 into x3, this path minus 2 by 9 into this x3 multiplying. So this is minus 2 by 9 into x3. So output y of t also satisfied. This is the state diagram by using Jordan canonical forms. The Jordan canonical form generally has the following properties. What is the properties of the Jordan canonical form? The properties are that the elements on the main diagonal are the eigenvalues. So these three are eigenvalues. -2, -2 and -5 are eigenvalues. These are eigenvalues. All the elements below the minor diagonal are 0. So this is the diagonal and 0, 0, 0, 0 below. All the elements are 0. Here r times minus lambda 1 and r minus 1 times 1. This is called the Jordan canonical forms. Here 2 times -2 -2 and 2 minus 1 times 1. This is the Jordan canonical theory. Then the ones together with the eigenvalues from typical blocks called the Jordan block, and this block is called Jordan block. This is the Jordan block because r times repeated roots and r minus 1 times this one. So this is Jordan block. State diagram of Jordan canonical forms. Here the system matrix is Jordan canonical forms, and also observe that had separate parallel path been used for the terms 1 by s plus 2 whole square and 1 by s plus 2 whole to the power 1. One unnecessary integrator would have been used because in this position s power 2. So 2 integrator, and for s plus 2 another integrator. But if the system matrix is canonical, then it must be avoided, which means minimum number of components, that is integrators. So this is the minimum number of components, which is integrators. So one integrator less in this position. This is the major advantage, and this is the signal flow graph for this block diagram. So ut equals to what? Ut equals to input. Ut equals to input, and x2 dot integrate x2. This is the x2 dot. This is the x2 dot in this position. This is x2 dot, and this is equivalent to x2. And this forward path 2 into x2 minus 2 into x2. This path minus 2 into x2, and this is the ut path. So x2 dot equals to minus 2 into x2 plus u of t. First equation satisfied. And this is the second part, x1 dot integrate x1. So this is x1 dot integrate. This is x1. This is x1. x1 also multiplied by minus 2, and this is the minus 2 into x1 minus 2 into x1 plus x2 plus x2. This is the x2 path. Again, for this situation, this is the minus 5 feedback, and this is x3 dot integrate. X3 dot integrate. This is x3. So x3 multiplying by minus 5 and minus 5 x3, only minus 5 x3, and this is the ut. So all the equations are satisfied. This is the signal flow graph. What is the output? Output y of t equals to 1 by 3 into x1 plus 2 by 9 into x2, and this is the 2 by 9 minus 2 by 9, and this is the x2. This is x2 path. This is x2 path, and this is x3 path. This is x3 path. So this is the signal flow graph for Jordan canonical form. Thank you.